Hello, and welcome back to Physics 41 University Physics 3. We are now on the last lesson for Chapter 7. So before we proceed, let's first review the previous chapter, wherein we discuss the force on current-carrying conductors exposed in a uniform magnetic field. So if you have a current-carrying conductor exposed in a uniform magnetic field, the force on that conductor is just equal to the length of the conductor and the cross product of multiplied by the cross product of the current and the magnetic field vectors. It will also have a magnitude of ILB sine phi, where phi again is the angle between the current and the magnetic field vectors. Again, we will still use the right hand rule. So for this lesson, for the last lesson in this chapter, it's actually quite related to this. Uh, in this lesson, we actually just focus on straight current carrying conductors. Actually, we had semicircular, but now we will now form a loop. What happens if you now have a full loop and you expose it to a uniform magnetic field? So that will be the focus of this last lesson for the chapter, the magnetic force, and we will introduce a new concept, the magnetic torque on current loops. So this is an example of a current loop. So basically a current moving around in a loop. So the current in this segment here is in this direction. The red direction is for the current. This is also immersed in a uniform magnetic field B, the one in the green directions. And using right hand rule, the forces in this segment is in this direction, and in that segment is in the opposite direction. Similarly, in these other two segments here, the force will actually cancel each other out. So in a current loop, the total force is actually 0. Now, for example, we have a side view of this loop. So even though the total force is 0, since this side of the loop is exerted by this force here F, and this other side of the loop will be exerted by this force, say F. But even though the forces cancel out, but this will cause the loop to rotate. So there will be rotation, there will be torque. So even though the total force is 0, but the net torque is not necessarily 0 for a current loop. So the force exerted on current loops, which sometimes we call a solenoid, actually creates a torque. It creates a rotation. So torque in this case is just the magnetic dipole moment crossed with the magnetic field V. We have discussed about the magnetic dipole moment before when we discussed the first lesson for this chapter. They are just when I introduced them as the tiny magnets and everything. So basically, a current loop is a magnet. So the upper half of this loop is the north pole. The lower half of this loop is the south pole. So in this case, if this is your loop, it has a certain number of turns. This will be the north pole, and this will be the south pole of the loop, essentially making it a magnet, and it has a magnetic dipole moment in this direction. So the magnetic dipole moment is actually, in this case, for current loops, is just defined as the number of loops, n. N is the number of loops. I, of course, is the current, and A is what we call the area vector. So A is the area vector. So basically, it's just the area enclosed by the loop, and its direction is always perpendicular to the loop. So it's always the area vector direction is always perpendicular to the loop. So if I, for example, if I draw a current loop here, a circular current loop, the area vector will be it's either out of the page or into the page, but it's always perpendicular to the loop. So in this case, you will notice that the direction of the magnetic dipole moment is actually the same as the direction of the area vector. Okay. So from here, we can now solve for the magnitude of the torque as just the magnitude of the magnetic dipole moment, NIA, magnitude of the magnetic field B, times the sine of the angle between the magnetic dipole moment and the magnetic field, which is, in this case, is phi. Okay. So again, zero net force on current loops, but the net torque is not necessarily zero. So one application of torque on current loops is the DC motor. This is actually the heart of every machine. So your car, your motorcycle, your electric fan, any motor has this principle. So it's a current loop exposed to a magnetic field, or a current loop and a magnet essentially creates a motor. So you usually supply the current in the current loop by the current in the current loop is supplied by a battery. So you connect it to the battery, there's current flowing through the loop, you place a magnet there, and then the loop will turn. And this is connected to your engine, the engine will turn, and your engine is connected to your wheels or your fan, and the fan will also turn. So basically, the motor. So in an actual setup for a face-to-face class, if this is a face-to-face class, in the laboratory, you will actually be making a DC motor. But sadly, we can't do it yet because of the pandemic. But this is what is expected of you to in a normal face-to-face class. So you will be making your own very simple DC motor. So you just have magnetic coils. Magnet wires. You form it into coils, and then you connect it to a battery. And this is actually a magnet here, a very small one. It's actually a neodymium magnet. It's a very powerful magnet. And then you will create torque. If you will recall, torque tau actually depends on NIAB sine phi. So it actually depends on the number of loops, the current, and the area of the loops. So if you want to have a motor that has a very large torque or very fast rotation, then you need to have your number loops as large as possible, your current as large as possible, meaning you must need a very large battery, and then your area of the loops must also be as large as possible. But of course, if your area of the loops and the number of loops is very large, that will actually become heavy, and gravitational force might be no longer might be significant, just like what we had in the previous example, where there's a copper rod and the magnetic force and the gravitational force balances each other out. So you also need to take into account the mass of your system. It's very heavy, then it will also have a hard time rotating. So another application is MRI. So we have discussed this in the first lesson, magnetic resonance imaging. So the tiny magnets in our body, we have magnetic dipole moments in our bodies because we have current loops in our bodies. The current loops made by electrons in your atoms, in the atoms of your body. But we'll just elaborate on that when we go to the next chapter on the sources of magnetic fields. So let's just have a very simple example. So suppose you have a circular coil. Uh, it lies on the horizontal plane where the magnetic field is uniform. If the coil carries a current of 5 amperes, find the magnitude and direction of the magnetic torque on the loop. So magnitude and direction. This is actually a circular coil. In an actual, if this is a perspective view, but if you will actually look at a side view, the loop will just actually be, or your circular coil will actually just look like flat, like that. And the magnetic field is in this direction, and the area. By the way, to determine the area of the direction of the area vector or the magnetic dipole moment, we use right hand rule. If your fingers are the direction of the current in the loop, then your thumb points to the direction of the magnetic dipole moment or the area vector. So in this case, since our current is in this direction, it's counterclockwise, so our current actually here will be going inside here. It will be an X here, and it will be a dot here. So meaning the current is going inside the loop here, and it will go out of the loop here. So like that. So meaning the magnetic dipole moment is directed upwards, or the area vector is directed upwards. So in this case, it's 90 degrees. The angle between the magnetic dipole moment and the magnetic field is 90 degrees. And to solve for the torque, or the magnitude of the torque, in this case, we can already know the direction. Mu cross B. So cross product. Mu is your pointing finger, B is your magnetic field. So the torque is actually directed into the plane. So if the torque is directed into the plane from your Physics 21, if this is the direction of the torque, your thumb and the direction of your fingers curling around your thumb is the direction of rotation. So in this case, the direction of rotation is clockwise rotation. So the torque is into the page. So it's just NIAB, and then sine phi, and phi is 90 degrees, so sine 90 degrees is 1. So it's just NIAB. So you just multiply all of the givens. So there's just one loop, and the current is 5 amperes, and the area is pi, and the radius is given. It's 0.05 squared, pi r squared, the area of the circle. Magnetic field is 1.20 Tesla. Sorry, 1.20 Tesla. So the final unit for torque is Newton meter. So the magnitude of the torque in this case is 0.047 Newton meter. Its direction is into the page. So if the direction of the torque is into the page, the rotation is clockwise. Okay. So basically, that's the end of the chapter. That's the last lesson for this chapter. So as a summary, a magnetic field can act on moving charges. And if it's now a stream of moving charges, then you have current carrying conductors. And current carrying conductors can be straight or can form loops. If it forms current loops, the net force due to the magnetic field will be 0, but there will be torque, there will be rotation. So for the next chapter, we will be talking about the different sources of magnetic fields, and we will start with a moving charge. So I will see you again in the next chapter.